Well, the last 3 days have been pretty intense. We've introduced you to the area between two curves. We've seen some really wild regions. And we've also introduced you to two volume by revolution methods. First was the disc, and then the second was the washer. And we've really stepped up and answered the call because I don't want to underestimate how challenging and how thought-provoking these topics can be. And I've been really, really impressed. So basically, I've imported 3 pictures. I kind of summarized what we've attempted to do. The first one here on the left was just the area between two curves, and I kind of want to summarize that right now before we go any further. I want to keep the area between two curves as simple as possible. And when we set up these integrals, it is simply upper minus lower, period. And of course, we had bounds of A to B on that area. So just upper minus lower, nothing more complicated than that. Or we could do right minus left in case it was in terms of Y. And then we moved on and we started introducing it to revolutions. Okay, we started to revolve a certain region around the x-axis or some other vertical or horizontal line. And what you'll notice here is if I drew a slice for this region, it is touching the axis of rotation, which is indicated here as being around the x-axis. And as we revolved it, we created a solid circular object that we call a disc. You could think of it as a frisbee. It's got no hole in the center. And actually, that leads me to another conversation where we could make the argument that all discs are actually washers as well. They just happen to have an inner radius of what? Yeah, 0. So a quick recap on that formula. We know that the disk had an area of pi r squared, and if we add up the area or volume of each really thin disk, we're getting the integral, pi times the integral from a to b of that one single radius squared, okay? And then we graduated to the next level. And now we said, okay, here's my slice, but it's not touching the axis of rotation. We've got this gigantic gap in the middle, and so we had to take that into account. And so as we set up our washers, we said we're going to find the area of the outer circle minus the area of the inner circle. And that's how I try to visualize it, and that helps me remember what the formulas are. So we identified our outer radius, we squared it, we identified our inner radius and squared him, and that's what gave me my washer formula. All right, so after our first couple of days of volume by revolution, perhaps the one biggest thing I want to challenge you with is kind of taking your sketches to another level. And I think that's going to be one of the secret weapons we have as we, try to eliminate any careless mistakes that may rear its ugly head, because we certainly have a strong conceptual understanding. The only thing that's going to get us in the way is careless mistakes, whether it's, identifying the length of the radius or a setup or something, and it's usually all traced back to our sketches. So I want to really challenge you to invest your time and energy into that sketch. And if nothing else, just make them bigger than what they are. And because sometimes they're so small, they're not really useful. It's hard to draw the slice that we want to draw, and it's hard to draw those squiggly brackets and so forth. So then after we get that done, we're going to indicate the axis of rotation. Again, another good habit so that halfway through the problem we don't lose sight of what we're trying to revolve it around. And all slices are drawn perpendicular. All right, cannot emphasize that enough. Perpendicular to the axis of rotation. If your slice ends up being vertical, then everything's in terms of x. If your slice ends up being horizontal, then everything's in terms of y, both the bounds and the function. Okay, and then here's the next big question that pops into your head. Is my slice touching the axis, or is there a gap? So basically, if it is touching, you're going to work with a disc, and all you have is the length of one radius. If there's a gap, now we're working with a washer, and we're going to identify both the outer and the inner radius, okay? Now, and probably the most important thing that's going to separate us on these types of problems is just correctly identifying the length of each radii. All right, if we can get the length of each radii, we're going to be in great shape. And just set up an appropriate integral, okay, that measures the volume of the given shape. And like we said on the last slide, if it's a disk, don't forget your pi. We're integrating from A to B. You got your single radius being squared. And if it's a washer, again, don't forget your pi, and don't forget to square each radius individually. So I probably sound like a broken record, but I hope so. That's kind of my goal here tonight, to really get these drilled in. And so we're going to pull up some old AP questions and see if we're ready to tackle them. My big goals tonight are not only to introduce you and give you a little flavor of some AP questions, but we really want to focus on our setup. We also want to practice some calculator skills, and I do feel extremely confident in our ability to mechanically work out these integrals by hand. So we're going to kind of forego that in an effort to shorten up the video a touch. But we're working on the function y equals radical x, which we can certainly draw without the aid of a calculator. It starts at 0, 0, goes through 1, 1, it goes through 4, 2, etc. And then we're going to cut it off at the line x equals 4. Okay, so that means we probably got 1 here, 2 here, 3 here. And the first thing they want me to do is just to find the area of this region. Of course, the x-axis was another bound, so we're really, let's see if I can bring in a light color here. See if this shows up. You know, we're really referring to this region right here. And now it's time to go set up. I'm going to draw a slice, and that just represents the height of each rectangle. So I'm thinking the area is going to be the integral. It starts at x equals 0, extends until x equals 4, upper minus lower, x radical x minus 0 with respect to x, bang. And that's certainly one we could take further by hand. My next question here on part B, they're claiming that there's a value of h such that it comes in the form of a vertical line, and it can split region R into 2 equal areas. Now, we don't want to draw it at 2. What you'll notice is if I draw it at 2, the region to the right of 2 is certainly bigger than the region to the left of 2. So we're going to offset h a little bit. We're going to slide him, you know, closer to the 3. And so we'll say that's our mysterious x equals h. And so what I'm thinking is the area from 0 to h has to be equivalent to the area from h to 4. All right, and then what I can do, and I am going to go a little bit further with this one just to clarify, my antiderivative on radical x would be x to the 3/2 times 2/3. And what I'm doing is I'm plugging in a 0 and an h. And then same thing over here, we've got the 2/3 x to the 3/2, plugging in an h and a 4. All right, so go ahead, and I just want you to substitute the appropriate numbers and bounds in the appropriate order, clean them up, solve for h, and see what you get. Come on back and check with me. Okay, so here's how mine finished out, and I did everything in green once we left off. I substituted the h, and I substituted the 0. I substituted the 4, and I substituted the h. The next thing I did was I wanted to combine all my h's, so I added this 2/3 h to the 3/2 to the other side, thus giving me 4/3 h to the 3/2. And then I also said 4 raised to the 3/2 using my groundhog rule. I did the square root of 4 first, which was 2, and then I raised it to the 3rd power to give me my 8. The next thing I did was I multiplied both sides by 3/4. I wanted to try to knock off this coefficient, just isolating the h. I got a nice number 4, and then what I did is I raised both sides to the 2/3 power. And that knocked off the exponent, and I was able to isolate h, and that represents where I should draw the vertical line to split that area in half. Now, the last thing we've got to do on this particular region's problem, well, I shouldn't say that. I spoke too soon. We got to do 2 more parts here. We want to find the volume is if r is revolved around the x-axis. So that's not too bad. I want to go back and look at the first slice I drew back in part A. This slice, my question is it touching the axis of rotation? I would say yes. It's simply a disk, and the length of this one radius that's involved, the length is radical x. I think I accidentally hit the pause button, so I don't know if that came together nice when I started playing it or not. But anyway, so let's go ahead and set this one up. We're going to say for part C, we're going to say the volume, because it's a disk, we're just going to go from 0 to 4 on the x-axis. We've got our one single radius. We're going to wrap it up and square it. And boy, that really turns out to be a nice problem to work. Let's go back and take a look at D here. They said, hey, now we've got a vertical line at x equals k, and it divides region R into 2 regions such that these 2 volumes are the same. Okay? So we're just going to, again, it's not going to be the same as h, where it split the 2 areas in half. So we're going to just put on a vertical line x equals k right in here, and we're going to say the volume from 0 to k has to equal the volume from k to 4. And I'm going to use the appropriate volume formula. So let's just set that up. Let's say the pi times the integral from 0 to k of radical x squared. And of course, if you want to call that just x, be my guest. And that has to equal pi times the integral from k to 4 of radical x quantity squared. Of course, you could divide both sides by pi to eliminate those rascals, and then you just do your integrating and plug in your bounds and solve for k. Very similar to what you did in B. All right, I felt like that last slide got a little too messy, so instead of trying to do all parts A, B, C, D on the same slide, I'm going to break them up into several slides here. New problem, we've got, they have provided a nice sketch for us, so that was very nice of them. And we've got the parabola y equals x squared, we've got the horizontal line y equals 4, they've identified the shaded region, And we just want to find the region of R. And again, keep the area as simple as possible. All we're looking for here is we want to integrate. There's no pi, okay? Remember, there's no pi and there's no squared signs. All we're going to do is upper minus lower. Upper function's 4. If I want to draw my slice, it's right in there. Minus the lower function, x squared. I'm not going to square anything. Okay, now the bounds are interesting. Let's see, I needed to find out when those two functions intersected with each other, and that's going to be at plus or minus 2. So I could go from negative 2 to 2, or rather what I would suggest is let's double this area and just integrate from 0 to 2 based off of the symmetry we're working with, and that would be a great setup for area. All right, now part B. Now we're ready to tackle some volume here. And we're going to revolve region R around the x-axis. So I'm going to go ahead and I'm going to get my slice drawn here. And, again, it could be anywhere within that region. And what you'll notice is that slice is not touching the axis of rotation. Therefore, we are working with a washer. Okay? And we are going to have to identify the outer radius. And we're going to have to identify the inner radius here to set this one up. Now, as far as my outer radius, I think that's just 4 units. And the length of the little inner radius right there is going to be x squared minus 0, just simply x squared. So my volume is going to be pi times the integral from negative 2 to 2. And rather what we're going to do is we're going to change the lower bound to 0 and double the final answer. And I'm going to take my outer radius, wrap it up and square it, minus my inner radius, wrap them up tightly and square it with respect to x. Bang! There it is, volume around the x-axis. Now, you've done enough AP. We haven't done a ton of AP free response questions, but you've done enough of them to know by the time you get to part C or D, you're looking for a very nice challenge. And they've certainly answered the call here by giving us a very nice challenging question. What they want us to do is they want us to put some mysterious line, y equals k. Now, k is going to be greater than 4, so it's going to be above my region. So I'm going to put a line up here at the top. And I'm going to say that line right there is y equals k. And what we're going to do is we're going to revolve this region around line y equals k. And by the time we get done revolving this region around the line y equals k, we're going to have the same volume as we did back in part B. Now, I know we didn't finish part B. The answer that I got for part B was 256 pi divided by 5. And what I'm going to do is I'm going to simply call that alpha b. I'm going to call that alpha b just to kind of shorten it up here. And so what I'm going to say is if I revolve this region, again, I've got another washer because the slice is not touching the axis of rotation. My outer radius right here, I'm going to say capital R equals upper minus lower. Look at that rascal. Okay. Now my inner radius is going to be that distance. And again, upper minus lower. Okay, so we're ready to go set it up. We're going to say that, let's see, again, the integral from 0 to 2, we're going to double the pi, and we've got the outer radius, k minus x squared, wrap it up and square it, minus the inner radius. So you could, very thankful that they did not ask me to solve this one, and I just have to make sure that I set it equal to alpha b, or 256 pi divided by 5. We're going to set them equal to each other. And that's all we had to do. They said write it, but do not solve an equation involving an integral expression that could be used to find k. And that'll do it, ladies and gentlemen. All right, now in our third example, we're going to cover something totally new, and we're going to do a tremendous, very, very heavy emphasis on our calculators, okay? So very, very important that you've got those handy. They're right next to you. We're going to use them as we go so that when we walk into class tomorrow, we're very proficient with the buttons that need to be pushed in the sequence. And I just want to be very, we want to just get right to the point and be efficient. I have not shown you even question A yet because something needs to be done first. And you know where this question's going. You know they're going to ask you the area of region R. You know you're going to do the volume when you revolve it around something, whether it's the x-axis or some other horizontal line and maybe even a vertical line. But here's the bottom line. Because it is so calculator active, we need to get this intersection point. All right, so how are we going to handle this on the exam? What work do we need to show? How much do we actually need to show? And how much do we need to communicate to the person grading our exam? What we need to do is we need to set the two equations equal to each other on our paper. Okay? Then what you need to do is we're going to plug them into y1 and y2. on your calculator, and the window is always a big issue with me, okay? Again, I want to be very efficient. I don't want to have a window that's too big or too small. What I'm going to do is I'm going to use the same window they gave me. I'm going to manually set my window so that my x-min is negative 0.5. My x-max is about positive 2, and I'm going to use a scale of 0.5, okay? My y-min is going to be negative 0.5. My y-max is going to be about 2, and I'm going to use a y-scale of about 0.5 so that when I do hit graph, I'm looking at a very, very similar picture as what I've got right here on the exam sheet. And also, as far as mode goes, let's make sure, because we are working with a trig function, let's make sure we are in radian mode, and there are no exceptions to that. We will be in radian mode all year. Okay, next thing we want to do is we want to go to the second calc menu, which is above the trace button. We're going to find this intersection point. They're going to ask you 3 questions. They're going to ask you who's the first curve, who's the second curve, and then they want you to guess, of course. Now what's going to happen is the calculator is going to spit out that intersection, and we're going to say it intersects at what x equals 0.94194408. And what I'm going to do is I'm going to store that in alpha a eventually. And then also the y coordinate. You never know when we're going to need that y coordinate in case we have to revolve it around a vertical line. So write that down as well. 78305. I'm going to store that in alpha b. So what I mean by storing is I'm going to go back to my home screen, and I'm going to, as far as the calculator goes, now this number is already stored in x right now. So what I'm going to do is I'm going to tell the calculator, take what's in x, store it in a, and then I hit enter and it's done. And right now, this number right now is already stored in y. So I had to hit alpha y, and then I said store that in b. Hit enter. It was a done deal, and I want to make sure I got them stored in case later on in the problem I had to find another intersection, and I didn't want to delete these out of the memory bank. So this is what needs to be on your test paper to communicate to the grader what these values are, because as we go through the rest of the problem, I'm just going to refer to it as alpha a, and I want the person grading my test to know exactly what number I'm referring to. Okay, so now here we go. We're ready to rock and roll. They do want the area as we anticipated. I'm going to set up an integral that starts at x equals 0 and ends at x equals alpha a right there. Integral from 0 to a. That's all I'm writing. I don't have to write out the 0.941 yada yada. And I'm going upper minus lower. So e to the negative x squared minus, make sure we've got parentheses here wrapped up around this function. Without the parentheses, we've got nothing. And there's my setup, and of course evaluating it on the calculator is a piece of cake. So I want you to go ahead and try that, and then we'll see if we got the same answer. Okay, real quick review. Notice we did not have a pi in front. We do not have any of the individual functions squared, nothing like that. It's just upper minus lower. Now, one of the things that I did on my calculator, when I started on the home screen, make sure you're on the home screen, not the graphing screen, and we're going 0 to alpha a. I did y1 minus y sub 2, just so I didn't have to retype those functions a second time. The more times you have to retype them, the chances of making a careless mistake increase. How do I get y1 and y2? If you're not sure, go to the vars menu, and once you hit vars, you'll go over to yvars, and then hit the function option, and you'll have your y1 and your y2 there readily available. So I got a final answer of 0.591, and that's my 3-digit answer that I'm going to report. Okay, again, exactly as we anticipated, these questions typically are very predictable. We're going to find the volume, we're going to revolve it around the x-axis, so I'm going to indicate my axis of revolution. I'm going to draw my slice. The slice is not touching, so I'm working with a washer here. I'm immediately making that decision, and again, my slice is perpendicular to the axis of rotation. I need to identify my outer radius and my inner radius. And let's see, what do we got here? Distance from there to there is going to be e to the negative x squared power. And then that little itty bitty gap at the bottom is going to be 1 minus cosine of x. So there's my individual radii. Would have been more exciting if they chose a line other than the x-axis, but we'll take it. And let's see, volume's going to be pi times the integral from 0 to alpha a. I'm going to take my outer radius, I'm going to wrap it up and square it, minus my inner radius, wrap it up and square it. And I know you're sitting there thinking, I don't need to plug this into my calculator. I know how to do it. Well, I'm telling you what, this is where more points are lost on simply plugging it in. So we're going to take the time to do it. And as I get ready to go plug it into my calculator, this is what you're going to see on my calculator screen. And I'm not going to print this on my test booklet. Believe it or not, the AP exam absolutely has a strong disliking for calculator syntax, okay? So do not, what I have in blue, do not put that in your test booklet. All I'm doing is I'm just putting this on my screen here to show you what my calculator looks like. And again, I'm a big proponent of using y sub 1 and y sub 2 just to cut down on the chaos and the chances of a careless mistake. So let's see what I get for an answer. All right, without the pi, I got 0.55 6 times pi, okay, or I could multiply that rascal by pi, and let's see what I got. I got 1.747, again, rounding to 3 decimals, always reporting 3 decimals on my final answer. All right, you guys are troopers. Good job hanging in there. This is going to be our last problem that we discuss. Again, very, very heavy calculator, very calculator active. This was a problem from it's near and dear to my heart. It was the area volume question the very first year I ever taught AP Calculus, and there was a big bear trap on this one. And what I want you to do right now is I want you to hit the pause button, and I want you to try to graph this function right here, and really work hard on getting the appropriate window so that you see the entire function. That's the big bear trap on this one. And I'll tell you right now, if you rely on Zoom Standard only, or if you rely on the window we had from the last problem, we're going to be in big trouble. So work hard, see what you come up with. All right, as far as typing these into the calculator, when you go to type in this function, don't be afraid to use alpha F1, which is a great shortcut menu that allows you to enter the function as a fraction, eliminates the need for the parentheses and so forth. Now, I ended up going with a y max of about 25 so that I could see the y-intercept of 20, and it's kind of like a bell-shaped curve almost. All right, and then of course we've got the horizontal line y equals 2. We've got these two gorgeous intersections, and the graph is very symmetric, even though my graph may not do it justice. Now to get those intersection points, I'm going to set them equal to each other, and you can do this one on the calculator or algebraically by hand. What you're going to do is I'm probably able to do it a little bit quicker just by hand, but that's my personal preference. I got 10 equals 1 plus x squared after I divided everything by 2, 9 equals x squared. So my intersections are at 3 and negative 3, so I don't really have to worry about storing them on this particular problem. So good sketch, identify those intersection points and make sure that your y max is high enough so that you see the y-intercept up here. Otherwise, if you don't go high enough, you're going to start to think that the curve's asymptotic to the y-axis and that there is not an enclosed region. Okay, so as far as finding the area, again, very predictable question. There's no pi, there's no squares. We're just going to integrate from negative 3 to 3, or what I'd like to do is just integrate from 0 to 3 and double my answer. And I'm going upper minus lower. This is my slice right here, and the length of that slice simply represents the length or height of my rectangle. So I'm saying 20 divided by 1 plus x squared minus 2 with respect to x. That'll find my area for me. And again, it's not too bad to plug it into your calculator. If you are going calculator option, don't be afraid to use y1 and y sub 2 just to cut down on the nonsense and chaos that you have to type in. Okay, our last one for tonight, we're going to revolve it around the x-axis, and I'm going to draw a slice within my region. It's not touching the x-axis, so again, I've got a washer. The outer radius here is going to have a length of, let's see, 20 plus 1 plus x squared, and the inner radius is going to have a length of 2 units. So my volume, again, I'm going to shorten up my integral. I'm going to go 0 to 3, double it. And then I'm going to go outer radius, make sure we have the appropriate parentheses here. We're going to square it minus the inner radius squared with respect to x. And ladies and gentlemen, boom, there it is. That integral will find the volume for you. And then from there on, you just rely heavily on your calculator and just making sure you're able to manipulate it very efficiently to get the right answer. And tomorrow in class, I'll hopefully have a little more exciting radii for you. That'll make you think a little bit more than what these AP questions are. I think they'll be a little more challenging, but I think we're ready to rock and roll and really put the big finishing touch on area volume. So good luck, and we'll see you tomorrow.